today we are going back at it again with quantum mechanics, and I am going to talk about uh, generally some of the discrete mechanics. But this is what makes quantum a little bit weirder than classical physics. Um, so don't worry if you like a lot of it sounds weird or hard to understand at first. This might be normal, but let's get into it. So, the focus is going to mostly be on discrete or quantized orbits, and we'll get into that in a minute. The next step would be on quantized radiation. And last bit, we'll talk about some quantized spin, and I plan on adding a few extra examples to elaborate things at the end of each section. But let's get into it. Alrighty, so quantized orbits. What does this mean? Well, quantized orbits have discrete orbits. So in the case of say if we have the planet Earth, whatever that looks horrible. But imagine that you have some spaceship going around the Earth. Now, normal rocket physics would tell you that you can orbit any orbit you want. You can go this way, go all over the place, and go here, and it's continuous. Because okay, sorry about that. It's continuous because you can have any amount of orbit that you want. You can have, you can orbit here, you can orbit here, you can orbit here, and there's no restriction. But this is no longer true in quantum mechanics with electron orbitals. And I could get into where this idea comes from, the origins of it, but I don't want to make this too complicated, so we're not going to go into that just yet. Maybe another day. Point is that these electrons have discrete orbits. So what does this mean? Well, we can see here that this one, we'll call it n equals to 1. And this, we'll say it's n equals to 2. The n, I don't know why they use n, but here n is like the orbital, the energy orbital. And you may have seen diagrams like this with the Bohr model in a chemistry class, and it is a quantum model. It's not the most complicated. Might get into that more about that later with wave mechanics, but not just yet. Right now this is baby stuff, and the point is that these electrons can only exist on these orbitals, this one or this one. There is no such thing as n equals 1.5. That doesn't exist. Or n equals to 3.14159. That doesn't exist here. Hang on. Let me clear that up. There we go. And that's not how this works. To give an example, as you can see here in this equation, En is the energy of the system. It depends on, the orbital. And why is this important? Well, suppose that this is some atom. Let's say, I don't know, it's hydrogen 1 atom. And let's say that we have a photon, say of red light. Red light comes in and interacts with the atoms. In order to even interact with these atoms, it has to have enough energy to make it go straight from there to there. Let me change that color, make it more noticeable. From here to here. If it doesn't have enough, if it only goes that far, then that doesn't work. And obviously, if there's no energy, then that doesn't help. Mathematically, we'd say that the energy is equal to like negative 13.6 divided by n squared. By the way, this value is not universal. It's only particular to hydrogen, and it might change depending on the atom you're using, but we're not worried about that right now. Just thought I'd drop that in. And in order to get enough energy, it has to have this particular amount. I can't remember, we could calculate this in a minute, but if it's less than, if energy or the photon of the light is less than negative 13.6 over 4, I can't remember the electron volts, this is the energy this is corresponding to, then there will be no transfer. But also if it has a little bit extra energy, if it's a little bit more than that, then it doesn't work either. It has to be exactly equal to, otherwise it won't work. And this is, it's a little weird compared to classical physics, but this is what makes it different. We can actually go over an example of this where it's used. You might have heard of spectral lines. You might have suppose that we have some some gaseous material made of some element, maybe oxygen, and we'll hit it with every wavelength of light there is. Oh, that yellow does not show up right, but we'll hit it with everything, and because the oxygen can only absorb certain frequencies of light, we might only get a little bit out and none of the others. And that scientists, for example, if they're analyzing some unknown material, they can analyze the radiation that comes out of this to determine what element it is. This is it for now. Could go into more detail later, but we'll do that another time. And if all you want to learn about is like quantized orbits, then we can do this. This is where you would end. But if you want to continue to quantized radiation, then we can continue.